Okay, so what I've done now is I've plugged my SpectroViz spectrometer into my computer, and I've opened up software, which is this Vernier spectral analysis software. And this window opens up here that says spectral analysis, absorbance, transmittance. I can close this window uh, or I can compress the window. So I can do an absorbance experiment, a transmittance experiments, fluorescence. We can do all sorts of things with this software. But you can only do these experiments if you have the correct instrument. For this instrument, we can do absorbance and transmittance spectra. So here, I'm going to choose absorbance here, and we're going to do a full spectrum to get a full spectrum of a solution. So I'm going to go ahead and select that. And it's thinking, thinking, thinking. I'm looking inside of the SpectroViz, and what I'm doing is I'm looking for a little light inside of here to show me, oh, there you can see the light, to show me that it is indeed hooked up. And what I'm going to be putting into that instrument are these two solutions. This is the blue colored solution, and this is the clear solution that has the same pH as the blue colored solution. Right now, this is warming up. We want the lamp to be warm so it has a nice, even intensity light. And you'll notice it says, place a blank cuvette in the spectrometer. So here's my blank cuvette, and let's see if I can show you this. Has no color in it. And so this blank cuvette will be measured as having zero absorbance or 100% transmittance. And I want to make sure I put this window here in facing the light. So I put the cuvette in, and I'm going to finish the calibration. So right now the instrument is sending light through the cuvette, and it's saying, okay, that's zero absorbance, 100% transmittance. And now you can see that we are ready to collect. Now, if I collected on this sample here, we would get zero absorbance and 100% transmittance, and the graph will be all wonky. So we're not going to do that. What I've done now is I've taken that sample out, and now I'm going to put this sample in. And this sample in, as you can see, has a little bit of color. So I'm going to put that sample in, and I'm going to hit collect. Okay, you can see that the graph appears very quickly, and it doesn't seem to change. It's still collecting information. So I'm just going to go ahead and stop. When I stop it, what will happen is this graph will adjust itself so it's full scale, so that this 0.2 is probably going to be at the top of the scale instead of 1.4. So I'm going to press stop. And you can see indeed that the place where absorbance is the greatest, we get something that's pretty full scale, okay? Because whenever you draw a graph, you want to use the full graph itself. You don't want to have a bunch of it where you just don't use it. Okay, so this is what the spectrum looks like. Okay, you can see the wavelength over here. You can see the absorbance. I can even click on the graph and find out where the absorbance is the greatest. And it looks like it's right there at 614.8 nanometers. So that's something I'm going to write down for the blue solution, 618 or 14.8 nanometers. And we might be able to move this over just a touch. And actually, we can see that here, the reading here is 0.156. So at any of these readings, 6114, 6113.6, we're getting a reading of 0.156, and that's the maximum. I'm going to choose the 614 because it's a nice even number and it's easy to remember instead of trying to get 61.8. Okay, so that's the wavelength at which there's a maximum absorbance. Now, I want you to imagine what this graph would look like if we diluted the solution twofold. That is to say, the concentration were half as much. So the path length is the same, light's going through the same amount of solution. The solution is going to appear to be less colored because the colored molecule, the bromothymol blue, has been diluted. So that means less light is being absorbed and more will be transmitted. So how much light would we expect to be absorbed in the case of a solution that's half as concentrated? And the answer is we'd expect it to be an absorbance of half of 0.156, which would be what? 0.078. Okay? So we're going to try and do that. We're going to try and make a solution that has half the concentration of the original solution and see if its absorbance is indeed 0.0156. So I'm going to go ahead and pause this now while I make this dilution. And actually, let me show you the tools of the trade for making the dilution. So the tools of the trade are going to be as follows. I want to have a nice test tube to put the solutions in. I want to have a tool for measuring how much solution I'm going to put in to the test tube. And I want to have two of these, one for the colored solution and one for the standard solution that has the same pH as the colored solution. To use these, I use a pipette bulb to draw a solution into it. And what I'm going to do here is I'm going to draw solution into this and read the measurements here and put it into my test tube, and then I'll mix it. So to make a twofold dilution, I want to use the same amount of each. Now, the cuvette holds about 2 milliliters of solution. And I don't want to make just 2 milliliters of solution because I'm going to take that first dilution and dilute it again, but I also want to be able to use some of it. So rather than just make 2 milliliters, I'm going to make more like 6 milliliters, which means I need about 3 milliliters of the standard solution and 3 milliliters of the same pH solution. So here I'm going to switch my screen share back to here so that you can see. Oops, let me put this back. Got to put everything back in its proper place. Okay, so here you can see the solution I'm going to dilute with and the original solution, and they both are 0.01 molar sodium hydroxide. Here you can see the test tube that I'm going to put this into. There it is. And here you can see the pipette. Okay, so I'm going to go ahead and start with this solution here. I'm going to open it up. I'm going to put my pipette into here, and I'm going to draw some solution up into the pipette with my pipette bulb. Now, this is something I'd be showing you how to do in class if we were meeting face to face. Okay, so right now I gotta wet the tip of my finger so I create a better seal with the pipette. And this is not really the best technique, but you can see that this goes to 5. And so what I'm going to do to get 3 milliliters is I'm going to drop this to 1, 2, 3. I'm going to drop this to the 2. So here you can see the solution dropping because I'm releasing tension on my finger or pressure on my finger. And right there, we're at 2. So I'm going to add this solution to my test tube, and I'm going to let it flow, and I'm touching the tip to the inside of the test tube, and I'm going to let it flow till I get to the 5. Okay, there we go. And I'll let the rest of the solution, actually it's not quite there. There we go. Okay, So I'm going to put the rest of the solution back. And I'm going to close the solution. And here I have 3 milliliters of the blue solution. Now what I'm going to do is I'm going to take 3 milliliters of this solution and dilute this. So I have a fresh pipette here. And I'm going to draw solution in. And here, you can see I don't need to drop it to 2. Right now it's at 1. No, not quite 1. It's at 1.4. So if I drop this to 4.4, I will be adding 3 milliliters of solution. So I'm going to drop this to 4.4. And there we go. So the nice thing about these pipettes is because they have lines everywhere, I don't have to go from 2 to 5. I could go from 1 to 4, and that's 3 mils. I could go from 1.1 to 4.1, and that's 3 mils. And I don't have to go exactly from one line to another. Okay, so there we go. Made my dilution. And what I'm going to do here is I'm going to mix this. And to mix the test tube, you basically put it in between 3 fingers and you tap the bottom of it and you get this little swirling action in the bottom and it mixes it very, very well. Okay, so now what I'm going to do with this is I'm going to take this and I'm going to put it into a cuvette. So here we go. Here's the cuvette. I'm going to pour a little bit of it in here until I get close to the top. So here, we're pretty close to the top. I'm going to cap it to prevent evaporation because evaporation will change the concentration. And here's my blue solution. Okay, so that's one dilution. Now I'm going to do it again. Now, to do it again, I'm going to take my pipette here and I'm going to squeeze out all of the solution that's stuck in the tip. Okay. And normally what I would like to do with this is I'd like to rinse the inside out with a little bit of this solution first. Okay. But we're not going to do that because I don't really have much of this solution. I'm going to take this solution and dilute it. And what I'm going to do is I'm going to rinse this out a little bit. So here I'm going to pull some solution into it. And what I'm going to do is I'm going to let that solution roll around inside of here. And what I'm doing is I'm rinsing the pipette out with the solution I'm going to put in there. So this is something you can do at home if you've got dirty glassware and you don't want to wash it. If you rinse it 3 times and nothing comes off of it, then when you put something in there, it's good to go. I know it's kind of disgusting. Now, this is my final dilution. So I don't need to make 6 milliliters of it. I only need to make about 2 or 3 mils. So I'm going to actually try and make 3 mils of it. So I want 1.5. Well, actually, if I've got enough here, I'm going to make 4 mils. So I'll use 2 mils of this and 2 mils of the diluting solution. So let's see how much I have in here. Well, I don't have quite 2 mils. I'm getting air bubbles into my pipette, and that's no good. So this is about the maximum I'm going to get. So I'm looking at the amount here, and I've got 3.7. So I'm going to drop this down to 5 into a fresh test tube. So 3.7. Well, I'm going to stop it right there. That is a little more. Okay, 4.7. So I actually put 1 milliliter into my test tube. Okay, that's good. Now what I'm going to do is I'm going to take the diluting solution and use precisely 1 milliliter also. So I make a twofold dilution. So with this one, I don't need to do any rinsing because I can just use the same pipette I had before. Okay, so here we go. I need 1 milliliter of this solution. So I'm going to draw some in. And I am at 2.1. So I'm going to go to 3.1. So here we go. And done. Okay, so I need my second dilution. And here, it's kind of hard to mix these when you have such a small test tube. So I'm going to go ahead and put it into the cuvette and pour it all in there. And then pour it back. And then pour it all in there. Now, with this particular dilution, you'll notice that it doesn't go all the way to the top. But that doesn't matter as long as the level of solution is high enough so that the light goes through it. And this is high enough. So I kind of like that this is a different volume than my other dilution because I can tell which is which based on volume alone. And so here are the two dilutions that we have. And you can see this one here that I'm kind of pointing at is looks a little lighter blue. Now I see that there's a little bit of an air bubble stuck in here. I don't want that, so I'll get rid of that. And then what I'm also going to do is I'm going to make sure that all of my glassware is dry. There's no solutions on the outside. And then we'll set up our calibration curve. So I'm going to pause this for just a moment, and then we'll continue with the experiment. Okay, so now I'm going to show you how we apply Beer's law to determine the concentration of an unknown, of a solution, a blue solution of unknown concentration. So I'm going to open up my Vernier spectral analysis program, and I'm going to share that with you. This will take just a moment. Before I share that with you, I'm going to share the instrument with you. So here's my SpectroViz. Here's the original blue solution. Here's the solution that has half the concentration. Here's the solution that has half the concentration of the half concentration. And here is the dilute solution, or excuse me, the solution that is the same pH as the other solutions. And here's the unknown solution. So if we take a look at each of these solutions, the concentrations are 0.0080 grams per liter. And for this one, since it's a twofold dilution, it's 0.0040. And this is 0.0020. This, of course, is 0.000. And this is, well, we want to find out what the concentration is. Okay? You're going to be making these calculations to show that the dilutions do have those concentrations. So I'm going to put these up right here. And now I'm going to share the program with you. So new share, and here is the program. We're going to do a Beer's law calculation here. And when it asks us, do we want to let the lamp warm up, we will say no, because the lamp has been going pretty well here for the last few minutes, so it's already warmed up. Actually, we can wait this 15 seconds. So I'm going to show you how to set up the calibration curve and the information that you get, and then we will determine the concentration of the solution where we don't know its concentration. Okay, so I have to put the blank in. So here's the blank. No color. Finish the calibration. So the blank is setting for 0 absorbance right now. Okay, so now I'm going to remove the blank. The blank is gone. And I'm going to put in this first stock solution. And here you can see the color. So this is the one that is the most concentrated. We're going to put that in here. And the desired wavelength is going to be 614 because we found that that wavelength worked pretty well last time. So I've set the wavelength. And we're going to go ahead and collect. And now I'm going to keep this number here. Actually, I'm going to make sure it's clean. Interesting. It seems like it matters which way I put this in. Okay, so we're going to keep this data here. The absorbance is 0.115. It's changed a little from when we did this earlier, and I wonder if it's because I did something weird. And anyways, we're going to keep this data, and the concentration here is 0.008. Now this says moles per liter, but we know that's actually grams per liter in our case. So we're going to keep this point. I'm going to take this out, and I'm going to put another one in. And this is the one that's half the concentration. And we're going to keep this point and call that 0.004. Keep the point. And the last one here. And that one we'll keep, and that's 0.0020. And I'm going to try that first one again, because it seems like it registered a little low. And here we go. See, that's more like it, the 0.130. Let's see if we can get rid of this 0.116 here. We're going to keep that point. 0.0080. And let's see, is there any way to get rid of a point? This one right here is the point we want to get rid of. Let me see if I can just delete it. Nope. Zoom to all data. We're going to do a stop. Now let's see if it'll let me get rid of that point. So I'm going to hit a delete, delete. Okay, there we go. So we got rid of that first point. The concentration is not there, so the point is no longer on our graph. And now what we're going to do here is we're going to apply a curve fit, and it's going to be linear, and so we're going to apply it. And so there's our curve fit. So when we write this information down, here's what we get. We get y is equal to mx plus b, and m is 15.69. And B is 0.005382, if I'm reading this right. Now I'm trying to think of why the slope is so large, or when I see why. Okay, so that's the equation of our line. And now I'm going to switch share to this. So there's the equation of the line. And remember, when we look at the graph, this was absorbance and this was concentration. So Y is the same as absorbance, and X is the same as concentration. Okay, now let's take a look at our solution of unknown concentration. So I'm going to go back to a different share. And so we're going to look at the graph again. And what I'm going to do here now is I'm going to take the solution of unknown concentration and put it into the instrument, and we're going to collect data. So we're going to append this. And for this new solution, we're going to see that the absorbance is 0.088. So we'll keep that. And here, we don't know the concentration. We're going to try to figure that out. So I'm going to cancel this. And remember that absorbance is 0.088. And I'm going to do a different share. So here's that solution of unknown concentration. I'm going to set this all off to the side. And we have for the unknown solution, that the absorbance is equal to 0.088. So our job now is to calculate the concentration of this unknown solution. And here's how we do it. Concentration will be equal to the absorbance minus 0.005382, and all of this divided by 15.69. And since the concentrations are in grams per liter, our answer will be grams per liter. So let's take a look at what we get for our value. So the absorbance is 0.088 minus 0.005382, and then all of this divided by 15.69. And so we get that the concentration is 0.00, and we're just going to round it to 1 sig fig, 0.005 grams per liter. Okay, so that's how we figure out the concentration of that unknown blue solution. So what I'm going to do now is I'm going to hit pause. I'm going to make up another set of dilutions for another experiment, only this time instead of using bromothymol blue in 0.001 molar sodium hydroxide, we're going to use bromothymol blue in 0.001 hydrochloric acid. And that's what the solution looks like in 0.001 molars hydrochloric acid. It changes color when the solution is acidic. So I'm going to set up those concentrations, and we will first get the absorbance curve to find out what wavelength to work at. And then we'll get the absorbance data. I'm not going to have the computer graph it, or the application graph it. I'm going to make you graph it yourself, and that'll be part of your assignment. And then you're going to have to determine the concentration of the unknown solution. Okay, so I'm going to pause this, set up the dilutions, go through it, and see what we get. All right, where's my pause? Okay, so this is bromothymol blue. Remember, BTB stands for bromothymol blue. This is bromothymol blue in 0.001 molar HCl. And the concentration of bromothymol blue is 0.0080 grams per liter. So this is the same concentration as the solution that we had in the 0.001 molar sodium hydroxide. Now, to make this dilution, I took 6 milliliters of the stock solution and diluted it with 6 mils of 0.001 molar HCl to a final volume of 12 milliliters. And this is that dilution here. Now, you can see I made 12 mils of this, and this is only about 2 of it. So what I do with the other portion, well, I took 5 mils of that, and I diluted it to a final volume of 10 mils with 0.001 molar HCl. So this is the second dilution right here. This is the control for this experiment, which is 0.001 molar HCl. So the same HCl as in the rest of the solutions. And here's the solution of unknown concentration. So what we're going to do is we're going to first use the stock solution to find out what wavelength we should be working at. And then we're going to collect absorbance data for these 3 solutions at that wavelength and construct a calibration curve. And then we're going to submit the unknown solution to the spectrophotometry, find out its absorbance, and from its absorbance, figure out its concentration. So let's take a look at the Vernier analysis here. I'm going to switch my share. And we're going to go with a full spectrum scan. And let's see, toggle full screen. Let's see what that does. Okay. So we want to go ahead and let the lamp warm up a little bit. And then what I'm going to do is I'm going to follow the directions here. And put in the blank cuvette. So this is the blank cuvette. I'm putting it in, and I'm going to finish the calibration. Okay, the calibration has been done, so I'm going to put the blank cuvette away. And now I'm going to put in the stock solution. So here's the stock solution. You can see that it's pretty concentrated looking. And we're going to go ahead and get a full spectrum. So let's take a look at this full spectrum here. Oh, I have to push collect. So I've got this full spectrum. I'm going to put stop. And it looks like the maximum absorbance is somewhere around, let's see, 426 nanometers. And let's see, indeed, 462 at 426. So 426, 425 is my maximum absorbance. And let's go ahead and I'm going to write that down here underneath the stock solution. Absorbance is equal to 0.462, and that is at 426.1 nanometers. And now what I'm going to do is I'm going to go ahead and collect some more information. So here is the next dilution. And for this one, the absorbance is equal to, let's see, we need to collect data. And I want to change the wavelength. I want the wavelength to be right there around 426. So 426.1, it's 0.231. 0.231 for the absorbance. Or actually, it's changed to 0.233. Okay, now I'm going to stick the next solution in here. So this is the second dilution we're looking at. Let's see, and here you can see it's at 0.108. Okay. And lastly, I'm going to put in the solution of unknown concentration, and its absorbance is at 426.8 is 0.089. Okay, so let's take a look at these again. And let me show you the data that I've collected. So I'm going to do a new share, and we're going to look at the cuvettes again. So here they are. Put this off to the side. Maybe I'll turn this light off for just a moment. I actually like that light on. And I'm going to turn this light off. Okay, so here are the 5 cuvettes that we used. Now here, the absorbance is equal to 0 because that's the calibration. So we're working at 426 nanometers for each of these different solutions. And the absorbance for the stock solution is 0.462. The absorbance for the first dilution is 0.233. The absorbance for the second dilution is 0.108. The absorbance for the control here is 0, of course. And the absorbance for this solution is 0.089. So you're going to take this information and you're going to build a calibration curve using this data here. You're going to make a calibration curve. Calibration curve or calibration plot, whatever you want. You're going to get the equation of the line. And then you're going to use that to get the concentration of the unknown solution. So I'm going to repeat that. With this information here, you're going to make a calibration plot. You're going to get the equation of the line. So you want to draw the line of best fit. And then you want to get the concentration of this solution. Now remember, for this guy here, the concentration of bromothymol blue is 0 grams per liter. And you can use that as one of your points. Let me lower that a little bit. So this is to tell you that the concentration of this is 0 grams of bromothymol blue per liter. Okay. Other things that you're going to have to do, of course, is you're going to have to find out this concentration by doing a calculation and this concentration by doing a calculation. And all of that's going to be outlined in your assignment. Okay, the last thing I want to show you is I want to put these off to the side. I want to show you this solution here. So this solution here looks kind of like the blue solution, but it's got a little bit of a different color. Actually, I'm not going to use this solution. I'm going to use this solution here. So let me show you the blue solution. So here's the blue solution. Here's the yellow solution. And this is also a bromothymol blue solution. And it looks to be green. So what we're going to do with this is we're actually going to get the spectrum of this green solution and see what's up. So I'm going to put some of this in my cuvette and rinse it out a little. And there we go. It's filled up. And I'm going to put this in my spectrophotometer. And let's see what we get for a spectrum. So here, I'm going to clear both of these. I wonder if there's a way to just clear all of that. At any rate, I've got to do a new share so that you can see what I'm looking at. So what I'm going to do here is I'm going to stop this real quick. And I'm going to see if I can close this. Don't save. I got to find a way to open up a new file without closing the darn application. And because I closed the application, screen share has gone away. So I'm going to go back. I just reopened the app. I don't know why I call it an app, but I guess it is. So here we're going to do the wavelength full spectrum. And the lamp is going to warm up a little bit. And we're going to finish the calibration. So I put in the, we're going to skip the lamp warm up. We're going to finish the calibration. I put a blank cuvette in. Now the lamp is plenty warm already. Okay, so we've calibrated it. And now I'm going to put in that green solution and let's see what we get here. Okay, and now I'm going to push stop. So this is that green solution. And if we take a look at it, it's different than the other solutions. It looks like we have, if you will, two peaks here. And let's take a look at yet another solution here. So here's another solution. Boom. And let's collect. And you can see the same thing going on. It looks like there's some absorbance here in the blue region, violet, indigo, and there's some absorbance in the yellow region. And of course, the red never seems to show up at all because we can't really see above 650. So interestingly enough, for these two solutions that we're looking at, this one here and this one here, they're both green. So how did I make that green solution? Well, it turns out I took some of the blue and I mixed some of the yellow in together. And what does blue and yellow make on the color wheel? It makes green. So our solution is green, but why does it look green? Well, if we take a look at this graph here, you can redraw this in your lab notebook, especially this red one. It turns out really well, and match up these little humps here with the different lines. And what would our explanation be for why the solution looks green? Blue and yellow make green isn't the answer. So I'm going to let you ponder that. And that's the end of this demonstration for this lab. So I'll be posting the assignment and you can have at it. Thank you for listening.